Let us now take a closer look at welding equipment, beginning with welding machines. There are three basic types of machine used in SMAW processes, namely AC machines, providing an alternating current to the output, DC machines, providing a direct current at the output, and AC-DC machines, providing both AC and DC outputs. Here we see a typical example of a light-duty AC welding machine. Featured in this unit are welding lead connections, a current adjusting control, and a current indicator. This particular machine has a current range of 40 to 140 amps. You may also come across even simpler machines that do not have current adjusting controls or indicators. In this example, the electrode lead connects to one of several tapping points. Each tapping point offers a fixed output or amp rating. AC machines generate alternating current to perform the welding process and are ideally suited to shielded metal arc welding and general-purpose work. Featured here is an example of a typical DC welding machine. Direct current is most suitable for welding thin steel plate, but is also used extensively in other industrial applications. Let us explain some important aspects about DC welding machines. In a DC circuit, the flow of electrons moves from a negative connection to a positive connection. On DC machines that have their lead connections marked plus and minus, we would normally connect the electrode lead to the minus terminal, that is, the negative terminal. The work lead would therefore be connected to the plus or positive terminal. In this configuration, the circuit polarity is said to be straight. However, with DC circuits, we can still operate when the leads are switched over, with the electrode lead connected to the positive connection and the work lead to the negative. In this configuration, the circuit is considered as being reverse polarity. It is the ability for the welder to change polarity that makes a DC machine more versatile than AC. For example, when welding thin plate, the welder would use straight polarity, as this generates more heat in the electrode, but less on the metal, and this prevents burning holes through the plate. Thick metal plate is best welded using reverse polarity, as more heat is created in the metal than on the electrode. In this way, a deeper penetration of weld can be achieved. Some types of machines have a polarity switch that makes the job of changing polarity easy. It must be noted, however, that a machine must be switched off before polarity can be changed. The ultimate type of machine for all arc processes is a combination AC-DC machine. This particular machine features the following: an isolation switch, used to start and stop the machine; a current selection switch, used to select between AC and DC output; an amperage control wheel, used to adjust the output current; an amperage indicator that displays the current setting in amps; a temperature warning indicator that shows if the machine is getting too hot; and welding lead connector sockets into which the two welding leads are attached. You will find similar controls and instruments on other makes of combination welding machines. All mains-powered machines should display information about that machine, needed from the welder's point of view. First, the welder must know what input power is to be used. This is sometimes called the primary side, and refers to the power requirement needed to operate the machine. Machines may operate at specified voltages on single-phase or three-phase supplies. The welder will also need to know what outputs the machine will provide. The outputs that concern the welder are the current output in amps, the current type, the machine's duty cycle, and the open circuit voltage. Let's look at these one at a time. Current output is simply the welding current available from the machine. This is usually given as the maximum output available. The current type refers to AC or to DC at the electrode. The duty cycle. The duty cycle of any welding machine is all about preventing the machine from overheating. When a machine is operating at maximum output, it will get very hot in a short period of time. If operated for too long at this output setting, the machine could burn out. Manufacturers use a period of 10 minutes as the basis of calculating a duty cycle. Duty cycle is given as a percent factor. For example, the duty cycle of this 250 amp machine is given as 30%. This means that it can be operated at 250 amps for 30% of a 10-minute cycle. In other words, the machine may be operated for 3 minutes at full output. It must then be allowed 7 minutes of cooling time or idling before it can be operated for another 3 minutes, and so on. If, however, the machine were to be operated at 140 amps, then its duty cycle is 100%, or continuous. Operating a machine below its maximum output extends the duty cycle. In other words, it can be operated for longer periods between rests. Most manufacturers supply either a duty cycle graph or print duty cycle information somewhere on the machine, from which one may determine the duty cycle at a given output setting. Note that some machines employ a cooling fan. The fan operates only when the machine is switched on. For efficient cooling, such a machine should remain switched on during the cooling periods. The last piece of information mentioned is the open circuit voltage, or OCV, as it is usually known. Open circuit voltage is the voltage available at the leads, or output connections, whilst the machine is switched on. Open circuit voltage is necessary to start an arc, but for safety reasons, the value is kept as low as possible, usually around 50 to 80 volts. We have looked at some of the features of typical welding machines. However, it must be impressed upon you that you should make a point of studying the operator's manual for the machine that you are using in order to familiarize yourself with its controls and limitations. Let us now look at welding leads or welding cables as they are usually known. Welding leads are made in such a way that they are very flexible, so that the welder is easily able to move them, yet heavy enough to carry the high amperages that are associated with welding. The construction of a typical lead is shown here. You will notice that the conductor core is made using many strands of fine copper wire, and it is because of this that welding leads are very flexible. Leads are made in various core sizes, ranging from around 13 mm up to around 25 mm in diameter. The diameter of the core determines the maximum current that can be safely carried. The size of the leads must always be selected to match the maximum rating of the machine to which they will be attached. If you are in doubt about the correct size of lead for a particular machine, then consult the chart provided in the Learner's Guide. Note that the length of leads will also affect the size selection. Long leads offer greater resistance and therefore reduce the load-carrying capacity. Welding leads must be properly terminated using the correct type of terminals. For attaching a lead to a stud, then a suitable lug must be used. Lugs must be soldered or crimped. The machine end of the leads may be fitted with quick couplers that fit into a machine's output connectors. The electrode lead terminates inside the electrode holder. The conductor core is secured into the metal head section. Insulation is provided by the handle which slips over the lead connection. Further insulation is provided at the electrode end with replaceable nose insulation. Spring-loaded contact jaws create the electrical connection to the bare wire end of the electrode. A common method of attaching the work lead to the work, or to a welding bench, is to use a spring-loaded earth clamp, commonly known as a crocodile clamp. Some work leads, for example those used on a welding bench, are permanently clamped to a convenient part of the structure. The success of any weld is to a large degree dependent on the electrode selected or specified in the welding procedure. Electrodes used in SMAW processes are known as covered electrodes. Covered electrodes are identified under the AWS numbering system, that is to say, the American Welding Society. The specification, AWS 5.1, refers to covered electrodes for use with mild steel. An electrode is simply a length of steel rod, called wire, that is coated or covered in flux. The steel wire is made of low-carbon steel, and this serves two purposes, namely, being conductive, the wire permits the passage of the welding current, and being of similar material to the work, or base metal, the wire melts inside the arc and supplies filler material, or reinforcement, to the weld. As you learnt earlier, the flux coating burns with the arc to form shielding gas, and then slag, both of which protect the molten steel from reacting with the atmosphere. The size of an electrode is determined by the diameter of the wire. Common for general purpose sizes are 2 mm, 2.5 mm, 3.15 mm, and 4 mm. The composition of the flux covering of any given electrode determines the type of electrode and its suitability for specific applications. A very common electrode is the E6013 type, also known as a general-purpose electrode. Other electrode types are suitable for special purposes, such as out-of-position welds, and those designed specifically for direct current used on thin plate and pipe work. Covered electrodes must not be allowed to become damp, as this will destroy the action of the flux. Electrodes should be stored in a dry place, preferably inside a warming box or an electrode oven. The two main tools required by the welder are a chipping hammer and a wire brush. The chipping hammer is used to remove the coating of slag from a welding bead. The wire brush is required to remove deposits of rust and stubborn slag from workpieces. Other tools that are frequently required include a pair of heavy-duty pliers or tongs used to handle hot workpieces, a ball-peen hammer used for many tasks such as setting the work, and then various clamping devices used for setting up and for securing workpieces. The basic skills and procedures for performing SMAW processes can best be learnt in a welding bay. The welding bay consists of a steel-topped workbench. The work lead of any suitable welding machine can be attached using an earth clamp to the steel top, or may be permanently attached to part of the structure. Steel workpieces may be set down onto the metal surface, and as long as the metal is clean, welding can be performed on the work. Provision should be made in the bay for your tools and other accessories to be stored conveniently when they're required. This concludes the video section of program number 1. Please complete the exercises in your learner's guide before continuing on to program 2.